Hello. Today we're going to look at some more graphical applications of the derivative, and we're going to start by considering critical values. Which I will usually abbreviate by CV. To remind you, a function f has a critical value at x equal a if a is in the domain of f and f prime at a is equal to 0 or f prime at a does not exist. We have to start with something it's in the domain, and then if the derivative is at that value is either 0 or doesn't exist, we call it a critical value. Okay, so let's look at a couple examples here. Suppose I have f of x is equal to 16x to the 1/3 minus x to the 4/3. This is problem 1b in your worked out solutions. So notice here the domain is all reals, so anything that we come up with where the derivative is 0 or doesn't exist will be a critical value. My derivative is 16/3 x to the negative 2/3 minus 4/3 x to the 1/3 using power rules, which we write as 16 over 3 times the cube root of x squared minus 4 thirds cube root of x. And notice here, first thing you should recognize, f prime of x does not exist when my denominator is 0, and so therefore it does not exist when x equals 0. Since my domain is all reals, this is a critical value. We now need to determine when the derivative is actually equal to 0. So I will take this derivative and set it equal to 0. I'll solve by multiplying everything by the common denominator. So I'll multiply by 3 cube roots of x squared. That's the common denominator here. Just to remind you, the algebra. And multiply both sides by that. Obviously, 0 times anything is 0. Over here, this leaves me with 16 minus the 3's reduce, and I have 4 times the cube root of x squared times the cube root of x is x. So rather simple. We get 4x is equal to 16, so x equals 4. This is also a critical value. So this particular function has 2 critical values. Let's look at my second example. Suppose I have f of x is equal to the absolute value of 2x squared plus 4x minus 1. Again, the domain is all reals. There is no issue, no problem. So we'll take the derivative, and for this, let me remind you before I actually do this, the derivative of absolute value of x is x over the absolute value of x. So in this case, the derivative would be 2x squared plus 4x minus 1 over the absolute value of 2x squared plus 4x minus 1. And then we have to use the chain rule times the derivative of the inside, which is 4x plus 4. Now, The derivative does not exist when this denominator is 0. So when that's equal to 0, this derivative is not going to exist. This does not factor nicely, but that's okay. We've got the quadratic formula. X then would be negative 4 plus or minus the square root of 16 minus 4 times 2 times negative 1 all over 4, which is negative 4 plus or minus 16 plus 8 is 24. And since the square root of 24 is 2 square roots of 6, this becomes negative 2 plus or minus the square root of 6 over 2. These are critical values. Also, where does the derivative equal 0? Well, this first piece of the derivative is never 0. These match exactly except for the absolute value. So this value, when you put in any real number, this comes out to be, this factor comes out to be positive 1 if the inside here is positive. It comes out to be negative 1 if the inside of the absolute value is negative, and it comes out to be not existing if the inside is 0. And so the only way this derivative can be 0 would be when 4x plus 4 was equal to 0, which means x is equal to negative 1. So this is also a critical value. So in this situation, I have 3 critical values. Okay, one more example. Suppose I have the following. And this is 1h in your worked out problems. We'll look at a piecewise defined function. G of x is x plus the natural log of x squared minus x minus 1 if x is less than negative 1, and x cubed minus 2x squared plus x plus 3 if x is greater than or equal to negative 1. Now I will tell you ahead of time, this function is continuous everywhere, and so the domain is all reals. We won't have to check that. But that's my original function. My derivative is also going to be piecewise defined. 1 plus the derivative of the natural log is 1 over what's on the inside times the derivative of the inside. So that gives me 2x minus 1 over x squared minus x minus 1 for x less than negative 1. And the derivative of this bottom part, 3x squared minus 4x plus 1 for x greater than negative 1. You might say, what about when x equals negative 1? And for that, we don't know. I know the original function is continuous, but it may not be smooth. It may have a corner point. And if it has a corner point, then the derivative doesn't exist there. If it's smooth, then the derivative exists. So let's determine that. To do that, remember we talked about these things before. I have to look at the limit each side of the derivative. Limit x approaches negative 1 from the left. That would be the function 1 plus 2x minus 1 over x squared minus x minus 1. And that value comes out to be 1 plus, this becomes negative 3 over 1, which is negative 2. And the limit x approaches negative 1 from the right, 3x squared minus 4x plus 1, that is 3 plus 4 plus 7, 3 plus 4 is 7 plus 1 is 8. Since these do not match, that means that f prime at negative 1 or g prime at negative 1 does not exist. I have a corner point, hence x equals -1 is a critical value. Now, we have to deal with each individual part and determine where the derivative is 0. So, my first part, 1 plus 2x minus 1 over x squared minus x minus 1. I'll set that equal to 0. Remember, this first part is only valid for x less than -1. This is the domain we're dealing with. And so I go ahead and solve. X squared minus x minus 1 plus 2x minus 1 is equal to 0. Multiply everything by the common denominator. That gives me x squared plus x minus 2 equals 0, which factors nicely. X plus 2, x minus 1. X is -2, or x equal 1. Now, this is where that domain becomes important. X has to be less than -1, so therefore this is not a real critical value, not at this point. This is the critical value from this section. Looking at the other part, the second part, my domain, x was greater than -1. We have 3x squared minus 4x plus 1 equals 0. This again factors nicely. 3x minus 1, x minus 1. And so we get x is equal to 1/3 and 1. And both of these are in this domain, so therefore these are both critical values. So in the end, I end up with 4 critical values in this case. -2, -1, 1/3, and 1.